Alrighty, so the rock cycle. For the benefit of the folks online, I'm going to repeat a couple things that I just said to you guys here in front of me. Please bear with me. So I was just talking to the folks here about how we have finished minerals. Okay, we might have spent a couple weeks on them in lab, but in lecture it was, just a little bit seemingly. It was one chapter, and we took some stuff out of that chapter. For rocks, which we're beginning now, we're going to be talking about rocks, easily for the next month, if not more. Okay, you got three kinds of rocks. You've got three different processes to make, bare minimum, three processes to make said rocks. In that mix, we need to talk about volcanism. We talk about weathering and erosion. I throw in a little bit of geologic time stuff. So it easily envelops a good chunk of what's left of the semester. The conversation on any given rock type is no longer than, the one for minerals was, but there's so much tangential material, okay? So we will be talking about this for a while. And in the lab, unlike minerals that went on for 2 weeks or so, the rock labs are only going to get a week each. And what that means to you guys in geology at any rate is that the rock test seems like it comes right on top of the mineral test. It is 3 weeks later, but still, compared to minerals, it seems like it's really, really quick. Just from listening to you guys, your experiences over the semester. So, just a heads up, we're not to the mineral test yet. We will be. Earth science folks, again, you get off easy. You don't have the mineral or the rock practicals in lab. But for those of you in geology, it's coming, okay? And again, I'm never in lecture going to hold up a hunk of something and say, what is this? But I will talk about it. Oh, well, basalt and blah, 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 blah. And I'm hoping you'll have a picture of basalt in your mind as we're talking about that. Sandstone or shale or whatever it happens to be, okay? So that's how they cross over. We talk about them in pretty good detail here. But in lab, it remains, recognition, understanding the pieces, parts. With igneous, we talk about the minerals that make them. With sedimentary, we talk about the pieces, parts that make them. And metamorphic, we don't talk about a whole lot in general. So yeah. So like I said, just a bit of heads up as we transition here to rocks. You're like, oh, the rock cycle. I learned that in 3rd grade. You did. All right. Ideally, we're going to talk about a little more than you learned in 3rd grade, and then again in 8th or 9th grade whenever you took earth science. But yeah, ideally, like the scientific method, you've heard the rock cycle before, just like the water cycle. You've heard that a couple times, hopefully. But we'll add to it, I'd like to think. And the big thing I add, all right, and we talked about this already, is the definition of a rock. And more so, how it varies from the definition of a mineral. You might remember, hopefully, you will. I'm not asking you, Siri, what the definition of a rock is. You might remember, hopefully, definition of a mineral was 4 things: naturally occurring, inorganic, crystalline, and composed of a fixed set of chemical and physical properties, right? All right. So, on the test, and they are going to fall on the same test this semester, you're going to have to give me both definitions. All right? So you got to keep them separate. There's one big thing that differentiates a rock from minerals, and that's that a rock can be organic. Some sedimentary rocks have organic origins. I tried, when I first started this, to help you guys keep these separate in your heads. Like, I don't know, I thought it would be some big deal or something. So I changed the definition of rock a little bit. Instead of saying naturally occurring, I said naturally formed. I don't care if you say naturally occurring twice. That's fine by me. Why not start at the same? But for some people, if you need to differentiate it in your brain, feel free to say naturally formed or made naturally, whatever. I just need to see that natural, in all honesty. So naturally occurring, inorganic, or organic. Then this part is all new. Consolidated aggregate, composed of grains of one or more minerals and or organic material. I like the bullets for minerals. I like the sentence for rock. Naturally occurring consolidated aggregate of organic material and or inorganic material, mineral grains and rock fragments. Look at that. Still a mouthful. So naturally occurring, we already know what that means. Inorganic or organic. So what we mean by organic here is that some of these rocks were something alive in their previous life. Coal, we talked about already. All right, coal was a swamp or maybe a marsh. You see a vein of coal, you don't see those too often anymore, but you're driving down a road and there's this giant black band, okay? At some point in its life, probably a couple thousand years, that was a swamp or a big marsh. And all that organic material became compressed down in there, compacted down in there, and we call that now coal. There's a giant period of time in the geologic time scale called the Pennsylvanian and the Mississippian. Everywhere else in the world it's called the Carboniferous, but in America, you know, we like to be different. We narrow it down to those two states because they've got really, really great coal layers there. Carboniferous, of course, is referring to the huge carbon content therein. All right, but we cut right to the chase, and you know, we're recognizing that coal. We love our coal. Also, there's a couple other organic rocks. You'll see one other one. Consolidated aggregate. Well, that just means consolidate means bring a whole bunch of stuff together, right? And, well, that's what an aggregate is, a whole bunch of stuff. So, we're bringing a whole bunch of stuff together. Okay, well, what kind of stuff? And that's where the last bullet comes in. So I'd give 3 points to this one instead of the full 4 because, like I said, depending on how you write it, it's not necessarily 4 things. The minerals one is definitely 4 points. All right. So what are we consolidating? Well, we're consolidating grains of one or more minerals. Very evident if we're looking at an igneous rock, coarse-grained igneous rock. Remember that granite I just showed you guys a couple minutes ago? Sorry, you folks at home, you'll see it eventually. You saw those multicolored crystals, okay? Those are all different minerals or organic material. And yes, sometimes you get both, okay? Especially in your sedimentary rocks. You're going to get pieces, parts of old rocks that have been lying around at the surface, and then you're going to get bits of organic material too. Even your organic rocks aren't 100% organic material. So, you know, think about that swamp that we're going to turn into coal. There's a whole bunch of mud and stuff in there too, right? And that's like, you know, silts and clays, which are generally quartzes and whatnot. So, you know, nothing's 100% anything. So, definition of a rock, okay? The biggest changes, again, is the addition of organic into this formula, or into this sentence. And then otherwise, you need to describe what we're talking about. I need to see, you know, minerals, inorganic material, and so on and so forth. Questions about the definition of a rock and or how it differs from the definition of a mineral? Okay. As you may hopefully already know, there are 3 types of rocks. You got your igneous, your sedimentary, and your metamorphicals. I think I talk about each of these on a slide. Hold on, let me see. Otherwise, I'll talk about them now. Yeah. So, your igneous rocks. And this is just an introduction, folks. You're going to believe it. You're going to get at least a PowerPoint on each of these. So, igneous rocks are formed from magma or lava that has cooled. Somebody remind us, what is the difference between magma and lava?
lava is the one that's above the ground.
All right, I think I saw a hand over here. Can you tell us what magma is?
Inside the earth.
Okay, magma is when we're inside the earth. So it's the same stuff, at least at this level. All right, molten mineral mixture, as I like to call it, in that first lecture we had there. And we're just really talking about where it forms, where it cools. That's important because that's going to give us crystal size. Oh, and it says right here, forms inside the earth or at the surface of the earth. But good answers all the same, you guys. We did have to talk about which one was which, so. Cooling is how they crystallize. Crystals grow. Rocks grow.
I think like the slower they cool, the bigger crystals they get.
Yeah, they have more time to grow. It's always use the example of like a head of cabbage or a big head of lettuce. You know, the longer, or children even, the longer you let them grow, the bigger they get, right? You freeze them when they're young, then they're going to stay.
Oh, God.
Yeah, no. I'm not suggesting that to do that to children. I'm just saying. Cabbages, of course. All right. So igneous rocks. As I said, that leads to a conversation about volcanoes because that's how we get magma at the surface, called lava. Sedimentary. Sedimentary rocks, as I like to say, are basically the chicken McNuggets of the rock world. Okay, they're pieces, parts of this, that, and the other thing thrown together, presented to you as a new thing. All right. So all these bits and pieces of broken up rocks, and they get glued back together. They get squeezed and glued, and hey, it's a new rock. Depending on the grain size of those pieces, we have certain names for it, and it gets kind of annoying for you guys, but you get through it. It's fine. What's really frustrating is after you learn all that stuff, and then I give you a multiple choice question on the test that says sandstone is composed of which of the following grains? And I'll list silts, clays, sand, pebbles, and cobbles, and some of you will get that wrong. Why? I don't know. What is sandstone composed of, guys and gals?
Silica?
Sand.
Sand. Good. All right. Don't forget that. Because it's frustrating for both of us when you do. But yeah, it is. I think you guys overthink it, is what it boils down to. And you're like, I don't know, there could be. Nope, just sandstone is made of sand. All right? Now, what those sand-sized grains are, they could be silica, but they could also be sand-sized grains of, anything else. So, at any rate, it's just that. It's all the riffraff out there glued back together and given to you as a new rock. But, and this is where we get to have a little chemistry talk, sedimentary rocks can also grow in water. It's not as big a thing as it used to be, but there's those little, I think they call them magic rocks or magic crystals. You still see them at the toy stores when we had toy stores. Target aisle probably has them. Walmart has them. But you see this little fish tank with those multicolored little stalactite-looking things of sediment that grow if you leave it set in your thing, and what you find out it's poisonous water, and if your cat drinks it, they die. And they're horrible things, but it's really cool, magic trick to have at home. Rock candy. Maybe you've made rock candy or seen rock candy or not enjoyed rock candy. It's not very good. But you're familiar with it, all right? That is sugar crystals that come out of solution and grow around a stick or a piece of string. Same idea, okay? So we do talk about those a little bit. We always forget about those. But sediments can also, the word is precipitate, sediments can also grow in water, crystallize in water. But everyone thinks about, like I said, the sandstone, the shale, big guys. All right, so as you can understand, that gets a good chunk of time in lecture. Lastly, the metamorphicals. Metamorphic rocks are just that. They're rocks that metamorphosed. They were something and now they're something else. We'll spend some time talking about how that happens and what changes happen because of it. Basically, you're going to do one of two things or both. Well, you're going to do one or both. You're going to expose a rock just to high temperatures. Take a piece of limestone, you bake it, you get marble. You take a piece of sandstone, you bake it, you get marble. You get quartzite, and so on and so forth. You'll learn some. That's just temperatures. The crystals grow bigger, they grow together. You got a new, more durable, usually more pretty rock. You add temperature into the mix, and really weird stuff starts to happen. You get those cool swirly rocks and a handful of other things. You can get temperature without pressure, but you cannot get pressure without temperature. So like I said, it's one or both. And that conversation will be so far away from now, don't fret about it. Okay.
Could you just repeat what you said though?
Not exactly the same way. What part did you...
Temperature.
So you can get temperature without pressure, but you're not going to get pressures. By the time you're getting the pressures, it's already got to be heated up too. So it's like you can get temperature without pressure, but you can't get pressure without temperature. And it's not, I don't say it's not relevant, but it's not totally not relevant now. The reason it's even important is because that's sort of how there's two types of metamorphic rocks. There's foliated and non-foliated metamorphic rocks. And the pressure is responsible for foliation. That's what gives us those cool swirly rocks. Okay? So that's why it's even relevant. But like I said, at this point in the game, that'll be, probably, I don't want to say December, but quite possibly the end of November. We're talking about stuff like that. So, long time from now. And yeah, I could never repeat myself verbatim. I get the gist of it. So those are your three types of rocks. And we have the wonderful rock cycle that ties all of those together. It explains how those rocks are created, how they're destroyed, and how they're recycled. Okay, Mother Nature was the first recycler. All right, everything is all the same. You could even argue that going back to the elements and stuff, and that's why we talked about it. All those elements are just recycled over and over and over. We're all stardust, baby. One of my favorite sayings from the 70s. Totally true, though. Okay? You only got so much material, and it just keeps getting recycled over and over and over again. Biggest thing out of this, I think that we add perhaps that you might not have got in earth science in high school. Definitely probably not in like third grade or whenever you talked about it the first time in life. But we add these processes, okay? It's almost like the arrows in between the little stopping points are more important than the stopping points. So I'm going to ask you to take like a half a sheet of your paper right now and draw what we're talking about. But do not start drawing right now, because we're going to kind of edit this as we talk. And there's a whole lot of squiggles on there, and the arrows are pointing to the wrong places, my opinion. So why do I even still use this and not just draw my own? Well, because it makes for a good conversation, teaching moments, whatever you want to call it. So, give yourself half a sheet of paper. If you don't have half a sheet left where you're taking notes, flip over, start anew. Or don't.
I'm drawing on my phone.
I think you're drawing it in your brain. It's all good.
Yep.
I know.
Do you want this paper? Nah, my photograph of memory.
She already offered. Thank you.
Don't waste the paper on me.
All right. So, thing is can you edit those photographs in your memory?
Yes.
That's the question. All right. So, at any rate, it's a cycle, it's a circle. There is no beginning, there is no end. I sort of pointed that out already, but we do need, conversationally, a place to start. So we're going to start at magma, all right? And I'm going to use a clock analogy. I never really figured out analogy and metaphor, which one, whatever, but we're going to call it an analogy. And so on this clock example, everyone says, 11 o'clock, 1 o'clock. You're supposed to look in that direction, you know what I mean? All right, so this magma, I want it to be 9 o'clock. on your little diagram that you're drawing, okay? And sedimentary rock across the way when we get there would be at 3 o'clock. You kind of see where I'm going with this? Metamorphic is at 6 o'clock. All right, just so we're all on the same page. So, magma. So draw a rectangle. Does not need to be 3D right now. Feel free to make it fun later. And in that, write magma, but I also want you to write lava. Just as a reminder, for those that aren't so familiar with this, that they're arguably the same thing. And then I want you to move up to 11 o'clock on this dial that we're making and draw the little rectangle there that is igneous rock. So at 9 o'clock, you got magma and lava. 11 o'clock, you got igneous rock. And of course, you will put an arrow in between them, but do not write the word solidification. Okay, so we've got magma or lava, and we're going to get to igneous rock. How did we tell you that magma or lava grows or turns into rock? There was a word we used. Not just cooling, but as it cools, what happens?
Outgassing?
Yeah, that's true, but crystallization. So instead of solidification, which just means make solid, let's say crystallization instead. That actually tells us something, okay? So magma or lava crystallizes into igneous rock. Oh, nice. All right, then we're going to take a big jump and we're going to move over to 1 o'clock on this dial. And you're going to make another rectangle that says sediment. And yes, you're going to write the words weathering and erosion on the arrow between 11 o'clock and 1 o'clock. Weathering and erosion. That one you can write what it says there. And off to the side somewhere, maybe below it, wherever you have room, we're going to take some time and define a couple of these words for the first time, perhaps. I need a couple somebodies to remind me what weathering or erosion is. Just pick one of them, anybody, and tell us one of them. Or what's the difference between, however you guys want to handle it.
Oh, weathering is when the rocks start to like break down.
All right, stop there. Somebody else. What is erosion then? She said weathering is when the rocks break down. I'm not agreeing or disagreeing with her, but somebody else. Yeah. Yes, Mr. Mahardy.
Erosion is when water runoff smooths down the surface.
Okay. So erosion is, one example of erosion is water smoothing down the surface. All right, in what way? How is it smoothing?
Over time, like runoff.
Does what though? What is the water flowing? I want to know specifically what you're having the water do. Is it moving stuff out of the way, or is it wearing down the surface?
Wearing down the surface.
Okay. All right. Somebody else. Add to both of those. Because they both need help a little bit. Yeah.
Weathering or erosion could be caused by any force, whether it be water, wind, sunlight, even if it's the right kind of rock.
Okay, yeah.
If you expose limestone long enough to even the sun, it'll start to disintegrate.
Yep, those are the agents of weathering and erosion, and we will talk about that. But that's not what I'm looking for yet. We need to differentiate between those two terms better.
I know I already.
Let's give someone else a shot. Hold on, though. Anybody else that hasn't spoken yet? Oh, yes, ma'am.
I would also say it has like particles of other things that participate in the process. So
Oh, helper, like tools.
like water transporting other like pebbles and wearing down.
The pebbles bash into something else and help. Okay, that's important. Not still exactly where I'm going, but that's you're closer. All right, what were you going to add?
Erosion is when when like water or wind or whatever like moves the sediments to like somewhere
Okay.
else.
All right, good. So this is a very common issue. I blame it on the I forget which antacid commercial it was, but where they have that little side view of the guy, the silhouette of the guy, and that red line going down his throat, and talk about esophageal erosion. And I know all the kids love to pay attention to those kind of commercials, but you see them so darn many times. And we're used to, and you come up the hill or you come across town from wherever school you came from, and we're used to using these words interchangeably. We're going to erode away the surface, and this is why I wanted to check. What is it, Liam? I'm just hard, but what was your first name? Liam. Yeah. Started at. That's why I was trying to pick it apart and get them to say one thing or the other. They're different. Weathering is the breakdown. Erosion is the transportation. So if he was having them clean off the water, clean off the surface by moving that rubble out of the way, then yes, that was right. But if he was just saying what I think he was saying, and in that it was smoothing out the rock even more, then that's still talking about weathering. So we need to make that distinction. Erosion is transportation. Weathering is breakdown. All right? So, like I said, somewhere on your little sheet, because you're going to see this on this test, and then it's going to show up on test 3 as well. You're not going to escape weathering and erosion. Shows up on the final again. Weathering is breakdown. Erosion is transportation.
Is erosion always the transportation of only the weather?
Yeah, it is the transportation of weathered materials. Yeah. Weathering is the breakdown of materials. No, I don't want to give you the big, scary definitions, but weathering is the transportation of materials. I just said it fast backwards. Weathering is the breakdown of materials at the surface of the earth. Erosion is the transportation of those broken down materials. So, that's where it is. And yes, you started listing the agents, as we call them in here. We'll talk about all that. They have their own chapter. It's that relevant. Looks like you got a question or a comment. Okay. Okay, so that igneous rock needs to be exposed at the surface, where it is exposed to these agents that we were talking to, breaks it down into smaller pieces, which are called sediments, by the way. So arguably, we could put erosion on the other side of the sediment arrow, but I don't want to totally nitpick this thing. Okay, but through the processes of weathering and erosion, this sediment is made and thrown in another word, deposited. We know what deposit means, but we talk about it in sedimentary rocks a lot. Okay, so we got a pile of dirt. My old office mate used to say, dirt's what you sweep off your carpet. You got sediment. Okay, fine. But we got either. So sediment to sedimentary rock, what do we got to do to make one into the other? Well, they've got it. Now you're at 3 o'clock. Right, next rectangle, write the word sedimentary rock in there. So we have the helpful term of lithification there. Lithification, to throw a little bit of Latin-glish at you. Lith is rock, and ification, like I like to say, is Latin-glish for turns to. Okay? You might know the word petrify more than you know lithify. We always use petrify as to think about something being turned to stone because of Medusa, and we read all those Greek myths when we're little kids and everything. Petrify, we also use to mean very, very afraid or scared, but and that you can't move. That's the thing.
Wood.
So,
All the wood, like trees that get petrified.
Ah, yeah, petrified wood and again, that's turned to stone. So we know that word a lot. Lithified is the sciencey version of that. Okay. So lith just means monolith. You've heard of a monolith? That's a big ass rock. Okay. So that's what lith means. So and as I said, ification is kind of turns to. So yes, sediment turns to rock to make sedimentary rock, but again, that's about as helpful as solidification is. So let's put a better word in there. You guys don't have a better word yet. We haven't talked about sedimentary rocks. So I'm going to tell you compaction and cementation. Squeeze them and glue them. Okay? Compaction and cementation. And yes, that doesn't cover the water ones, but we don't need to worry about them right now. We just want to make something slightly more helpful than turns to stone. Because, if we're going to make a rock, we want it to turn to stone. How do you make it turn to stone? So compaction was one of the words, and cementation is the other. So we have sedimentary rock now. We're going to go down, make our next box at 6 o'clock, write metamorphic rock in that box. And yes, we've got an arrow going from sedimentary rock to metamorphism. To metamorphic rock, and we have the incredibly helpful word of metamorphism in there. Well, what did we talk about? This one's a lot closer in your memory bank, so I'll ask you guys. Metamorphism involves exposure to what and what?
Heat and pressure.
Yeah. So write exposure to heat and pressure, high temperatures, high pressures, whatever you want. But don't just write metamorphism. And just to add our last little arrow here finally, where they have the word partial melting, let's just write remelt. Because you want to turn a metamorphic rock into magma, you got to melt it. So let's not worry about the technical points. Oh, well, it doesn't completely melt. It's still, We'll talk about that when we get to metamorphic rocks. Right now, we know that we need to melt it again. So let's just call it remelting. So what we've just said then is magma or lava cools and crystallizes. You might want to add the word cools to crystallize if you think it'll be helpful. Magma or lava cools and crystallizes into igneous rocks. That igneous rocks at the surface can get exposed to weathering and erosion, which turns them into sediment. That sediment becomes compacted and cemented into sedimentary rock. That sedimentary rock can be exposed to high temperatures and pressures, which will turn it into metamorphic rock. If that metamorphic rock continues to get really, really hot, it will remelt and turn back into magma. Now, I'm going to tell you something that I wish my teachers would have told me, I don't know, as many years ago as I was staring at these stupid drawings. Okay? If you can't make a sentence or a story out of it, you don't understand it. You need to be able to explain that to your grandma or whoever. Okay? And because if you just look at it with these handful of words on there, yeah, you could probably memorize that for the test. But this is actually, like I said, the foundation for so much of what we're going to talk about. So when you are taking a couple minutes to look at it when you go to study for the next test, if you read it in your mind as a sentence, even if it's, separate sentences, you're going to have a much better understanding of it, and it will really help later. Okay? And the same thing goes for formulas. That's where I really first discovered this, was that if you substituted the words in for all those variables and then read that formula as a sentence with the right vocabulary in, actually makes sense. And I never would have believed that. I hated formulas. I still hate formulas. But I understand how to appreciate them now. But nobody ever said that to me. So I knew a variable had a vocabulary, it meant something. But, V or capital T or lowercase t, I know they all meant different things. But a formula is a sentence. That's all it is. All right, so now there's a whole bunch of stuff still on here. Let's address that. First and foremost, we're not going to deal with rock and mantle. We don't care. Okay? Just don't worry about it. So, of course, not every igneous rock breaks down into sediment and into sedimentary rock because, well, we know we have igneous rocks in the lab room. Not every sedimentary rock turns into metamorphic rock. Why? Because, well, we see all kind of sedimentary rock out on the surface of the earth and so on and so forth. And, well, not every metamorphic rock remelts into magma because, well, we know metamorphic rocks exist, so we've seen some. So that's what these arrows in the middle are all about. Not everything follows this. This is the outer loop. This is the main pathway, whatever you want to call it. But by all means, that is not the only options available. I don't like where these arrows go. These arrows go to the objects. I can't think of the right word I want to use. We want these arrows to go to the processes, okay? Because you can't take igneous rocks, for example, straight to a metamorphic rock. Well, no, it has to go to metamorphism. I know it's nitpicking, but since we're redrawing this, let's draw it in a way that makes more sense. So yes, an igneous rock could be exposed to high temperatures and pressures, which is metamorphism, and then turn into a metamorphic rock. So that arrow that comes out of igneous rocks and goes straight down-ish, make it point to metamorphism, the process, instead of to the rock that's already made. That's all I'm saying. Sedimentary rock. Again, this is a tiny little loop here, okay? But it is probably the loop that the majority of the rock, the surface of the earth, is caught up in. It's not exceptionally exciting to be a rock, okay? Best case scenario, you roll down a hill, you float down a stream, you see the world a little bit, and then you stop moving again. So this little loop over here, which should go to weathering and erosion, not back to sediment, okay? That is a big chunk of the active, the visual rock cycle. This is the surface of the earth in motion. All right, and like I said, while it might be the shortest arrow you're drawing, it's arguably the biggest loop. And it can get stuck in that over and over and over again. All right, the rock breaks down. If it's lucky enough, those pieces get brought back together. Hey, you're a new rock. Great, let's roll down another hill, and so on and so forth. So, sedimentary rock, weathering and erosion, back to sediment, metamorphic rock, same idea. Not all of them remelt, of course. Some of them get exposed to the surface, so we want to point that to weathering and erosion, not to the word sediment, because weathering and erosion makes sediment. So we're happy with, the general directions of things. We just want to redirect the arrows a little bit. Questions? Not to belabor a point, but all of these, solidification, lithification, metamorphism, those are all types of lithification. All right, and we kind of touch on this at the very end again to try and pull it all back together, but as I said, it's so time-wise, so far away from one another. So what we're really going to be talking about from here on out is how do you lithify igneous rocks? How do you lithify sedimentary rocks? How do you lithify metamorphic rocks? And you can very easily say, how do you make an igneous rock? How do you make a sedimentary rock? And how do you make a metamorphic rock? But it's science class. We want to use a sciencey word, so we're going to say lithification. Yeah? No. And you don't need to draw the arrows, but again, any one of the three rock types, you could have an arrow coming out of that circle, and that represents the rock sitting on your shelf at home, or the rock sitting on the shelf down at the end of the hallway, or the rock that is carved into a statue sitting in some Greek metropolis that's been there for, Acropolis that's been there for 3,000 years, or so on and so forth. If it's outside, arguably it's back in the system, but you know what I mean. It's not lying next to a set of railroad tracks or out in the middle of a desert. So you can take any one of these specimens out of the cycle. Yeah?
But we, like as humans, making it a bit more complicated because we're bringing rocks somewhere where they would appear.
Yeah. This comes up a lot more in environmental science than it does in here. But when we talk about the nature of natural systems and so on and so forth, I've always argued that humans are not part of that at all. I mean, we are because we're part of nature, but we totally mess with the cycle. Yeah, I agree. And that's even as far as, and not to go environmental sciencey on us, but the wonders that we have now of in January being able to get fresh tomatoes. Yes, they came from Chile, but they're here now. Well, how does that mess things up? Well, let's argue that they weren't grown in a greenhouse; they were actually grown in the soil. Okay, so that tomatoes and whatnot, they're supposed to die and go back in the soil, or at the very least, be sold, within a 10-mile radius. And that waste from that goes back in the cycle, the system, so on and so forth. But now we're taking these products and shipping them across not even countries, but continents and so on and so forth. So yeah, we're totally screwing up many cycles, and the least of which is moving rocks. But yeah, we're monkeying about with the system, pun intended. But we're smart little monkeys. We can make air conditioners and heaters, which allow us to go in all these cool places that we weren't supposed to go in the first place, and so on and so forth. So, to quote a old antiquated song, you cannot go against nature because that's the nature of nature. I think I just paraphrased it, but nonetheless, it's natural to go against nature. So, it is what it is. Before we get too more philosophic, anything else? Then we'll move on. Good. All right, rock symbols. Because there was a time when you could not just hold up your phone and say, Google, what the hell did they just say? We needed at some point some symbols that we could all share with each other to look at somebody's map from Sweden or Africa or China or North America and know what that other person was talking about. So we developed some symbology, okay? Some common colors and all kinds of things. And that's where these rock symbols come in. You are going to learn 4 of these, 3 of these, all right? But they're very, very, very helpful. These are the ones I need you to know. We got the bricks. We got the dots. We have the dashes. And we have my pitiful attempt at asterisks. The bricks are limestone. This is 4 points on the next test. Write them down. The dots are sandstone. The dashes are shale. And the asterisks are supposed to be crystals, so that's just a generic igneous rock. So you may find yourself thinking, why break down all those sedimentary rocks but just lump all igneous into one? Well, first of all, if we were in a position to care, I don't mean to say if we cared, somebody does. If we were in a position to care about igneous rocks, believe me, there are symbols for each of those, okay? Our studies, the main time we're going to use this, we're actually going to apply this later. That's why I introduce it now, is when we're talking about groundwater, all right? And the majority of the time when we're talking about groundwater, we're close to the surface and we're full of sedimentary rock. And depending on what type of sedimentary rock your water's coming out of, blah, 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 we care, okay? So we're drawing all these cool little layers and we're going to label the different rock types that way. So we're learning some sedimentary ones. Again, superficial geology is way more understandable than the deep subsurface stuff, like if you're worried about oil drilling or gas drilling, okay? So this stuff is even, you're likely paging through a textbook, you're going to see these things. Yes, sir?
Can you repeat the name?
Yeah. So the bricks, let's let everybody do that one. What's the bricks?
Limestone.
Limestone, good. And the dots?
Sandstone.
Sandstone, beautiful. The dashes?
Shale.
Shale. And then the last one?
Igneous.
Just generic igneous, yeah. And I I have a couple pictures to help you understand why we drew them the way we drew them. C is shale, yeah. B is sandstone. A is limestone. So why? Well, it kind of looks bricky, doesn't it? I don't know who took this picture, but it's totally like crooked. But it was beautiful. It showed the brickiness, so I kept it. But this is either a really warped layer that's going up, or they just held their camera really, really weird. That plant is sort of growing vertical, so I'm guessing that this is indeed a sloped layer. Otherwise, that plant would kind of be off to the green one, not the red thing. But these plants tend to kind of grow straight up. Anywho, so bricks for limestone. Shale. You've probably encountered shale out where you were wandering around as a kid. Okay, it's all thin and layered and breaky and everything like that. The real word for breaky is fissile. We'll worry about that later. But so that's why we use the dashed lines. Sandstone, of course, is all the little sand grains. Might not be able to see them with the resolution here, but you've felt it before. You know what it feels like. And I don't know if I have, I don't have any sparkly crystals for the other one, but again, picture somebody's granite countertop or something like that, and that's why we use the little crystally star sparkle things. This is something very, very common. I'm going to be talking about it a lot when we get there. All right. And I wish I had like a companion slide to go with this, that we would have a layer of dashes, then a layer of bricks, then a layer of dashes, then brick, dash, brick, dash, and another thick. Limestone and shale you see over and over again. If you've driven east on 90, okay, you're familiar with the Little Falls exit. It's on the cover of your lab book. Blew me away when I came here. There's such an awesome cliff, a road cut there. Right then and there's not a whole lot of the tan. If you keep going, you'll see the limestone get interspersed as you go along 90 a little more. Again, the limestone is the cream or the tan stuff there. Why you see this so much is that this is a shallow marine deposit. Okay, so near shore, salt water, and shale comes from, well, does anybody know what was shale when it was not lithified?
Oh, fossils?
No.
Oh, clay? No,
Yeah. I'm looking for just a colloquial term, what we would say. You wouldn't say, oh, I stepped in clay.
Shit.
Perhaps, depending on your grumpiness at the moment. How about something a 5-year-old might say that too? Mud, thank you. Mud, yes. Clay was not shit, or shale was not shit. It was mud, all right? And yes, sometimes it's clay, sometimes it's silt, sometimes it's silts and clays. Don't need to worry about it right now. But so mud, all right? So mud, and then the limestone is sort of, somebody said shells earlier. That's your shells, it's the limestone. They're dissolved. It's still mud, but it's calcitic. It's calcite based because it's dissolved seashells. So then you got that. And you're not going to have your seashells. Think about when you're walking at the shore, if you've been lucky enough to be at the beach. Okay, you're walking in sand, so you're not here anyhow. But you go out further, you're going to be in the muck. You can't stand there because it's too high, but it's there, trust me. It stops being sand. And so yes, if you're wondering, somewhere there's a sand deposit that goes with these that mark the shoreline. Okay, so anywho, the calcite then is where all the seashell critters live. They die, they fall to the bottom, they get all dissolving and mucky. And then all of a sudden, we're back to mud again. Like, wait a minute, what's happening here? This is shoreline movement, okay? This is sea level changing. And this is why people just, scientific sort of people just shake their head when they argue against sea level change. All right, if the whole submerged cities wasn't evidence enough, we've got the rocks all over the place that say, okay, this was this. So this is one point through time. You draw a line straight up that cliff, It's one point through thousands of years. And you were this deep, then you were deeper. The limestone is deeper, by the way. Shale is shallower, limestone's a little deeper. So you just go back and forth. It happens. It's not a big deal. What?
Shale is often an indicator of oil. We have oil in Western Europe. Is this because this big shale shelf stretches pretty much all across the state?
So, a couple things there. Because shale is shallow, it tends to be where life is close to shore. Oil is old life, be it dinosaurs or sea-shelled critters or whatever it was, plant-based fossil, fossil fuels. So because life tends to concentrate closer to the shores, I think that I didn't get into the petroleum end of things at all. I had a decision very early in life that I could sell my soul and go out on a ship and make a buttload of money, or I could teach. And so I never learned, and that's one of those things where you definitely learn on the job stuff versus, there were petroleum geology classes. They didn't interest me. I didn't want to do that from early on. But that's a historical person's view of things. I'm a historical geologist. So my idea is that because life concentrates there, that's why the shales tend to be more rich in that stuff, or at least indicators of those kinds of beds. That being said, the one at Little Falls is completely devoid of fossils. I didn't know that. The guy that I replaced told me, I was so excited. I'm like, oh my God, we take field trips there? He's like, you could go, but there's not a damn thing there. I'm like, what do you mean? It was an anoxic environment. For those of you that don't know what anoxic means, it was oxygen poor. It wasn't really good for life. There's a handful of reasons that can be, but end result, no critters, so no oil. But Utica Shale, which they tap in Ohio, which confused the hell out of me as well, because again, I don't do geophysics, but starting to wonder what I do because I keep saying I don't do this, I don't do that, I don't do that. Just think about how many flavors of doctor there are, okay? There's that many flavors of anyone else you talk to that's a scientist here. But I do surface processes and critters. I'm a paleontologist. But Utica Shale, they're pulling, I think that's the one they like to frack in. So again, the fracking is a different kind of drilling than you're doing with your standard traditional oil wells or your gas wells. And that's just trapped pockets of life in there, that died and we're extracting now. Be it good, bad, or indifferent, we're not going to worry and talk about the processes or the ethics of it or anything. But yeah, that's why shale's black, because it's so carbon rich.
Okay.
The answer's right there, even.
That's 25 miles from here. Alien Gorge has tons of fossils.
Oh, Ilian Gorge, okay.
Which is
Excuse
probably 10 miles or 12 miles there.
Higher or lower in the rock record is in the column is the question. And that's more the answer than anything.
And that's why up in the town of Russia, where they made that rock cut 30 years ago, they opened it up to paleontologists and archaeologists to go in there and do
Is it shale or is it limestone?
I believe that was shale as well.
Okay. Yeah, I mean, shale is we love it for fossils because it's so fine grained. Think of it as like video games, you guys. The fossils you get out of it are a function of the crystals that are preserving it. So if you want to make something press something in sand, you're going to get, let's say, this kind of relief. What's the word I want? What do they use with graphics?
Lithographic.
No, like the computer version of it. Resolution, thank you. The sand is going to give you one resolution. The silts and clays, way better. Because they're so much finer grained, you can get so much better detail. So that's why we love shales. They do tend to be fossiliferous for sure. And it was, like I said, a bad assumption that I made that they all were. And I think I was just more disappointed than anything that there was 100 foot of it that was nothing. But yeah, the fact that you could go up north or down south, more than likely what you're doing is traveling above it or below it in the rock record.
But that's still pretty, it's in the valley. But that's.
I'm not sure this is even New York City. I didn't take this picture.
But Little Falls is still in the valley. It's considered the Mohawk Valley.
Yeah.
Or you're going up and out of the valley. I don't know what the actual elevation is there, but it can't be that much higher than the Alien Gorge or lower.
I don't know. We can poke around and do a little research, but off the top of my head, I don't. I don't know. When I was young and still wanting to go out in the field and having fun, I had children, so I didn't. And I took them, to a few places, and believe me, they've done their share of rocking and fossiling and whatnot. But I didn't get to anywhere near, and I didn't grow up here either. So all that time when I again would have been in school and going out on field trips and stuff, I did that in Ohio, not here. So I hear from you guys over the years, and I learned about Whetstone Golf, Pixley Falls, a handful of those places. I still need to get to Moss Island. It's not fossils, but very, very cool. And the Hercs, I didn't learn about until I was 40, so. But I am learning. So, but my answer just off the cuff is it's, either a different puddle in the same ocean, and it is not anoxic for whatever reason, or it's higher or lower in the column. So, there's a couple of different reasons. The easiest thing to do is to check and see if they're the same age. This one is Ordovician. I don't know. It's inside the lab book. We don't need to belabor this much more right now, but it's really easy to check. New York State's been covered immensely. They have a great geological survey. So that'd be the quickest thing to do is to start with and see if they're the same age. If they are the same age, then you got more questions. If they're not, then that's almost the answer to your question right there. So, but yeah, I wish this was my picture. This is, maybe it is because I didn't cite it, but this could be anywhere. This is like I said, a very common thing. All right. So, 1042. What do we go to? Do we go to 11 or 11:15?
11.
There's a video I like to show right now, and I'm not going to get a chance to see it. So we'll either start next week with it, or maybe I'll assign it to you as homework. But it's not long, but it's not this short either. So we're done for today, I guess.